Hey everyone, let's derive the derivatives for trig functions today. And I kind of want to start it by looking at this uh, graphically. So often my want. Um, Here's a graph of sine from 0 to 2 pi. And I'm wondering what the derivative will be. Well, let's try the activity where we graph the derivative by approximating slopes. So here and here, the slopes look horizontal. And so I'm going to say at this point, the slopes graph, or the derivative of sine, would have a 0. And here, the slopes graph, or the derivative of sine, would have a 0. Now, I see over here that this is as steep as the slope gets on the sine graph. Still positive slopes, but these positive slopes are getting smaller and smaller and heading towards 0. So they look like this. Then the slopes over here are all negative slopes. This is as most negative as the slopes get. Near 0 negative, a little more negative. Oh, they're even smaller and smaller. This is the smallest slope, the most negative slope here. But then they start getting less and less negative, these slopes, as the slopes head back towards 0. So I think I have a minimum here where the slopes are smallest, most negative, and then the slopes go back to 0. From 3 pi over 2 to 2 pi, I see that these slopes on sine are all positive numbers. Not the y values on sine, the slopes on sine. A little positive, more positive, very positive. And so there's my graph of the derivative of sine. If sine was the original function, f of x equals sine x, then the derivative function, f prime of x, must be cosine x. Therefore, the derivative of sine is cosine. Ta-da! All right, well, let's see if we can do the others. Oh, actually, I wanted to do the more formal calculus-y approach to this derivative using the limit definition of the derivative. No, I'm never going to ask you to do it. If f of x equals sine x, but I do want you to see it, then f prime of x would be the limit as h heads to 0 of sine x plus h minus sine x all over h. Okay. Please, by all the gods living and dead, do not distribute this sine to this x and this h. This is a sine sum and difference formula. You cannot just distribute sine here. Instead, using that sine sum and difference formula, you would have the limit as h heads to 0 of sine x cosine h plus sine h cosine x. And don't forget our minus sine x. All of this over h. Well, what I want to do is factor out a sine x from these two terms and push this one to the side. So now this will look like the limit as h heads to 0 of sine x. This will be left over from this term, cosine h. When I factor a sine x out of sine x, I'm going to have 1 left over. And on the bottom, I'm going to have, nothing. Nothing yet, just the bottom will be that h. And then we've got plus sine h cosine x. and all of this is over h. Great. Okay, so now what I'm going to do is I'm going to split this up into some different limits. I'm going to say the limit as h heads to 0 of sine x times the limit as h heads to 0 of cosine h minus 1 over h plus the limit as h heads to 0 of sine h times the limit as h heads to 0 of cosine x. Okie doke. So let's see what happens. We need to evaluate. There's no h's here. So what do I get? Well, I get just sine x. But here, I have no idea what this is. And I don't have a shortcut for this. So I need to pull out my calculator. And I'm going to graph cosine h minus 1 all divided by h. And I'm going to, oops, I don't want zoom, I just want graph. There. As h approaches 0, what's the limit of this function? Well, it looks like cosine h minus 1 over h approaches 0 as x approaches 0 from both sides. So I'm going to say that this limit is 0 when I use a graph or a table. Plus, now, if I plug a 0 in here, the sign of 0 is 0. Why do I feel like I got a mistake? Oh, that's because there was a plus sign here, Mr. Cuckoo, you silly ninny. Okay, and so there's an h there. All right. So now what about plugging a 0 in here? Well, I get 0 over 0 again. So again, I pull out my calculator, but this time I want to do sine x divided by x as x approaches 0. And you may be already thinking, well, we know what this looks like, Mr. Koopa, because we spent some time talking about the limit as x approaches 0 of sine x over x. And we see that that limit is 1. So this is going to be 1 times cosine x. So 0 times this plus 1 times this gives me this. This is what my f prime of x is. This is the derivative of sine x. No, you won't have to do that on a test for us. Yes, if this were honors AP Calc, you would have to do this on a test for us. I just need you to know that the shortcut derivative of sine is cosine. Now, is that also true for cosine? What's cosine's derivative? If f of x equals cosine x, what would its derivative be? Well, cosine starts high, goes low, and back high again. Put in the 0 slopes. There's one here, there's one here, there's one here. So I've got a 0, a 0, and a 0. These are all negative slopes. This is as negative as the slopes get. They get less and less negative, and then the slopes head back to 0. So I would have something like this. And then over here, the slopes are always positive, a little positive, more positive. This is the steepest positive slope we've got. Then the slopes actually start getting smaller and smaller towards 0 again. So I think I got something that looks like this. So what is the derivative of sine? It looks like f prime of x isn't, I'm sorry, the derivative of cosine. It looks like the derivative isn't sine x, because sine would start here and go up. This is starting here and going down and then back up. The derivative of sine x is, I'm sorry, of cosine x is negative sine x. Okay, so we've got our first two trig derivative shortcuts. Sine's derivative is cosine. F equals sine x. F prime equals cosine x. F equals cosine x. And f prime equals minus sine x. All right, what about tangent? What if f of x equals tangent x? Well, tangent can be written as sine over cosine. And we know that this is a quotient. We've got some division here. The derivative of tangent is not the derivative of sine over the derivative of cosine. Not f prime of, not the derivative of sine over the derivative of cosine. This is not what the derivative of tangent is. That's bad. Don't do that. No, no. Where's my big pool noodle? This is worse than pool noodle if you do this. Stop it. Okay, so how do we figure it out? Well, we use the quotient rule. So let's sing our little quotient rule song. F prime of x is going to be low d high, the derivative of this, minus high d low. The derivative of cosine we just learned was minus sine, all over low squared. Okay, so let's tidy this up. We've got f prime of x equals cosine squared x, and negative times negative is positive. Sine times sine is sine squared x, all over cosine squared x. Well, remember from our Pythagorean identities that sine squared plus cosine squared equals 1. And 1 over cosine squared is secant squared. So when f of x equals tangent x, then f prime of x equals secant squared x. Okay? The derivative of tangent is secant squared. And yes, you're not expected to memorize this. I'm deriving it for you. I'm showing it to you in case you get stuck on a test somewhere in your brain will be this information. But this is what must be memorized and used all the time. I expect when you see, oh, hi, I'm tangent, you say, oh, your derivative must be secant squared. You really need to know them so that you're that comfortable with them. Okay, so let's take a look then at cotangent. F equals tan x, f prime equals secant squared x. So if f of x is cotangent x, we know that's cosine x over sine x, and we use to find the derivative, again, the quotient rule. Low d high minus high d low, all over low squared. And so when we tidy this up, we get negative sine squared x minus cosine squared x over sine squared x. And oh my God, if you cancel out these signs, I will chase you with a stick, not a pool noodle. Instead, let's factor out a negative from both of these terms in the numerator. So I've got my negative out here in front, and I've now got sine squared x plus, because negative divided by negative is positive, cosine squared x over sine squared x. Sine squared plus cosine squared is 1, so I have negative 1 over sine squared x. And we know that sine squared is cosecant squared, or 1 over sine squared is cosecant squared. So negative cosecant squared x is our derivative here. So when f of x is cotangent x, then f prime is going to be negative cosecant x, just like the derivative of tangent was secant squared. Ooh, not cosecant, but cosecant squared. Gotta have that squared or you're going to be very sad. Okay. The last two, what about the derivative of secant and cosecant? So if y, or f of x, equals secant x, what's the derivative of that going to be? Well, I know that secant is 1 over cosine x, and so I can use the quotient rule. F prime of x is going to be low d high. Low is cosine x. The derivative of 1 is 0. The derivative of a constant is 0. Minus high, and the derivative of cosine is minus sine, over low cosine x squared. So what are we looking at here? Well, 0 times this, that all goes away. Minus times minus is plus, 1 times sine is sine, and I get f prime of x, sine x on top, cosine squared x on the bottom. Well, I'm going to split this cosine squared up to sine x over cosine x times cosine x. And I'm doing this intentionally because I know that sine x over cosine x is tangent x, and 1 over cosine x is secant x. So when f of x equals secant x, f prime of x will be secant x tan x. So the derivative of secant is secant tangent. Okay, last one. And yes, we will do the inverse trig derivatives, just not today. So if f of x equals cosecant x, we know that's 1 over sine x. We use our quotient rule, and we get low d high sine x times 0 minus high derivative of sine cosine over low squared. And so 0 times sine, this goes away. Negative 1 times cosine is going to be negative cosine x over sine squared x. And again, I'm going to split up that sine squared x into sine x times sine x. And notice we've got cosine over sine with a negative, so that's negative cotangent, and 1 over sine is cosecant. So then we know that if f of x is cosecant x, the derivative of that would be negative cosecant x cotangent x. Now I'm wondering if you notice something about these derivatives. There's a bunch of them, yes, I agree. Well, look at all the co-function derivatives. All the co-function derivatives have negatives on them. Cosine's derivative is negative sine, cotangent's derivative is negative cosecant squared, and cosecant's derivative is negative cosecant cotangent. Okie doke. Excellent. So I thought we could do some practice problems at this point and go through and see how to use these derivatives in situation, in combination. So we'll do some of those and then we'll call it a class. Oh, by the way, you're going to need those derivatives I just erased, so keep them handy. All right, so let's start with 1. if f of x equals secant x times tangent x. Okay, so this is a product here, so I need the product rule. So f prime would be this times the derivative of that, secant x times the derivative of tangent. We know the derivative of tangent is secant squared x, plus this times the derivative of that. And we know that the derivative of secant is secant tangent. And so we can tidy things up a bit here. Secant times secant squared will be secant to the third. And here tangent times tangent will be tangent squared. You know, we could certainly pull out a secant. It's not going to get us anywhere. This isn't quite like our work with identities when we were in trig class. But sometimes those are useful to think about, which is why I'm musing on them now. Because in this case, secant squared plus tangent squared isn't anything. Secant squared minus tangent squared is 1. And I would definitely, if I saw this, turn this into 1. Because 1 times secant would be secant, and that would be a much easier derivative. But we just have this. And so that's as good as it's going to get. All right, let's move on. 2. 2 is x squared, oops, I should really start with f of x equals x squared cosecant x. So again, I see a product, so let's do the product rule. F prime equals this times the derivative of that. X squared times the derivative of cosecant is negative cosecant cotangent plus this cosecant times the derivative of that, which is 2x, using our polynomial shortcut. So, you know, I'm troubled by this because someone's going to turn it into a subtraction situation. So I really want to rewrite this a little bit. And I'm going to take out an x and a cosecant x. So x cosecant x, and we've got negative x cotangent x plus 2. Why factored form, Mr. Kukla? What's the big deal? Well, in Chapter 5, when we start doing word problems in serious manner with these things, we're going to be setting derivatives equal to 0 all the time. So that we can, when we set derivatives equal to 0, we need to then be able to solve. So we were going to factor and set each factor equal to 0. So we want to get accustomed to that process now, okay? All right, how about a quotient? How about f of x equals 3x over tangent x? Okay, so I know that the quotient rule is needed here. So f prime of x will be low tan x d high, the derivative of 3x is 3, minus high 3x times the derivative of low. The derivative of tangent is secant squared, and really you need to be able to do that without looking at that piece of paper. And over low squared, tangent squared x. Okay, not really going to be any tidying up we can do here, so I'm just leaving it and moving on. How about one more with quotient rule? F of x equals cotangent x over square root of x. Remember, square root of x is x to the 1/2 power. So if I use my derivatives, I know it's a quotient problem I'm looking at. So I do low d high. The derivative of cotangent is negative cosecant squared x minus high cotangent x d low. Now the derivative of this has to be done with the power rule. I bring down the 1/2, Leave the base alone and subtract 1 here. So, remember when we were doing all that factoring in pre-cal where we took out these negative exponents? Guess what? We can do that here as well. I'm also going to take out this negative symbol because it's troubling me in here. So I've got negative x to the negative 1/2. What's left over? Well, when I factor a negative 1/2 out, I just get x. And I have a cosecant squared. I took out this negative, I took out this negative, negative divided by this negative will be positive. I've got my cotangent x. I took this out, but I have my 1/2. And that's much tidier. Okie doke. Cool. Well, that's basic derivatives for us. Yeah, I think we're good to go. How about you try this gentle one? F of x equals sine x cosine x. So f prime. Think about that for a moment. I'll have a sip of water. Okay, so we know this is a product rule situation. So we want this times the derivative of that, sine x. The derivative of cosine is minus sine x, plus this times the derivative of that. And so we end up with minus sine squared x plus cosine squared x. Oops, not cosine of x squared, but cosine squared x. And no, that's not a Pythagorean identity, so we're just going to leave that alone. Okie doke. Well, welcome to trig derivative shortcuts, and I hope your homework goes well with them.